Let's try out finding the radius and interval of convergence for the sum as n goes from 1 to infinity of negative 1 to the n times x to the n divided by the cube root of n. As I said in a previous video, we are generally going to use the ratio test a lot of the time, not all the time, for this work. And so we've got, remember, the ratio test uses the absolute value, which for us means actually two things right now. One, I'm not going to write down the negative 1 to the n because we would drop it anyway. But number two, I got to keep the absolute value because we do have a variable x, which could either be positive or negative. The n plus first term is x to the n plus 1 divided by the cube root of n plus 1. And then we're going to multiply that by the reciprocal of the nth term. And so the cube root of n divided by x to the n. I'm going to combine the two radicals into a single radical of a fraction. We have the limit as n approaches infinity of the cube root of n divided by n plus 1. This is still going to be an absolute value, and I have n plus 1 factors of x in the numerator, n factors of x in the denominator. N factors are going to divide out. We have the limit of the, as n approaches infinity, of the absolute value of the cube root of n over n plus 1 times x. As n approaches infinity, n over n plus 1 approaches 1. And so this just becomes the limit as n approaches infinity of the absolute value of x, which converges if the absolute value of x is less than 1. That, folks, is the radius of convergence for this exercise. So for the radius, I'll say r is equal to 1. And I'm going to underline both of those statements, that the absolute value of x is less than 1 and that r equals 1, so that we don't accidentally lose them later, because we're not done yet. Folks, if the absolute value of x is less than 1, then that means that x is between negative 1 and 1, and that's the beginning of understanding our interval of convergence. But because we didn't have as plain a series as we did in the previous video, we have to test the endpoints. We do so separately. First, I'm going to remind us that the sum goes from 1 to n and is negative 1 to the n, x to the n, divided by the cube root of n, and I did that because I had to move everything out of the way here. We have two endpoints. One is negative 1, one is 1. And in both of these cases, we're referring to x values. And so we will consider the case that x is equal to negative 1. What happens here is we plug negative 1 in place of x in the sigma expression, and then test the resulting series for convergence. Replacing gives us the sum as n goes from 1 to infinity of negative 1 to the n times negative 1 to the n divided by the cube root of n. That first negative 1 to the n comes from the original expression. That second negative 1 to the n came from substituting x is equal to negative 1. At this point, we're going to combine the bases. So we have the sum as n goes from 1 to infinity of, it's negative 1 to the n times negative 1 to the n. That's going to be negative 1 to the 2n divided by the cube root of n. And if negative 1 is to the 2n, folks, that numerator is always positive. The result is that this diverges because it's a p series with p less than or equal to 1. You see, the cube root of n is n to the 1/3. Therefore, this the interval of convergence does not include x equals negative 1. Now we test separately for x equals 1. We're again going to replace the x in the sigma expression by 1. So we have the sum as n goes from 1 to infinity of negative 1 to the n times 1 to the n, if you like, or you could leave it out, divided by the cube root of n, which now is an alternating series. So this converges, and we can see it, but you can write out the steps for the alternating series test. So back up here, we have a radius of r equals negative 1 and an interval, which is, let me just move this out of the way a little bit, negative 1 to 1, not including negative 1, but we do include 1. Now, why did I underline this in pink? I was really just letting you know that that was the stage at which we discovered what the radius was. Everything after that we did was to determine the convergence behavior at the endpoints of the interval. Now we're going to look at a couple of quick ones, basically special cases. Same instructions, determine the interval and radius of convergence. We have the sum as n goes from 1 to infinity of n to the n, x to the n. And most of the time we'll use the ratio test, but folks, when I have these exponents of n, I'm going to use the root test. For the root test, we're looking at the limit as n approaches infinity of the nth root of the absolute value of n to the n, x to the n, which is equal to the limit as n approaches infinity of n times the absolute value of x. As n approaches infinity, folks, n approaches infinity, so n times the absolute value of x approaches infinity as well. That's the limit. It'll be infinity unless the base x is 0. So this is the case where we have a radius of 0 and our interval is the set that contains 0. For an example of the other special case, we'll look at the sum as n goes from 1 to infinity of x to the 2n divided by n factorial. Now we do have an exponent that includes an n, so we may be thinking root test, but with a factorial, I'm going to go ratio test almost all the time. The way the ratio test looks here is the limit as n approaches infinity of the absolute value of x to the 2n plus 2, I did write 1, x to the 2n plus 2 divided by n plus 1 factorial. That's what happens when we put n plus 1 in place of n in the sigma expression there, times the reciprocal of the nth term, and so n factorial divided by x to the 2n. All of the factors of n factorial divide out, and in the denominator we're left simply with a factor of n plus 1. We have x to the 2n is going to divide out, and that'll take out 2n factors of x in the numerator. We're left with x squared. This then becomes the limit as n approaches infinity of x squared divided by n plus 1, which is equal to 0. I have n in the denominator, and if n goes to infinity, that expression goes to 0. So this converges for all x. That means the radius is infinity, and the interval goes from negative infinity to infinity. So here's the deal with the special cases, folks. If the limit of the expression is infinity, then it'll only converge for the single solitary value of x. The radius is 0. The interval is whatever x is to make the base 0. I say that because you could have something like x minus 2 in here, right? Then the interval would be the set containing 2. Or you have a limit that's 0, in which case it'll converge for all x. There's not a way to make that not converge, and so it's all real numbers there. All of the other times, though, you're looking at a bounded interval, and you're going to test the endpoints.